Now we're going to talk about Carnot cycle. If you remember Carnot's theorem, the most efficient heat engine that can operate between two energy reservoirs is the one that is reversible. And so Carnot suggests the following cycle between these two energy reservoirs. So we have a hot energy reservoir that's at temperature TH, and then we have a cold temperature reservoir at temperature TC, and we can have two isothermal processes in which we will be extracting or releasing heat to these energy reservoirs. So operated as a heat engine between A and B, we have an isothermal expansion process. So that's the first part. And during this process, basically the gas is inside a container that has insulated walls. So we don't have heat exchange with the environment. However, we have basically a nice thermal contact here between the energy reservoir and the gas, and therefore we can basically absorb heat from the energy reservoir, and that will be QH. So A to B, the process between point A and point B, is isothermal expansion. The volume is increasing, and during this process we're going to absorb heat from the hot reservoir. So this is when QH enters the cycle. And from point B to point C, before going to the cold reservoir, we have an adiabatic expansion process. So what is adiabatic expansion? So everywhere is thermally insulated. So we have thermally insulated walls, as you can see here, and therefore we have no heat exchange with the environment. So Q is equal to 0, and it's an adiabatic expansion process. So what is going on in this process? Obviously no heat exchange with the environment. However, we are generating an area in the PV diagram, so therefore there will be a work done. So WBC. And then we're going to go through an isothermal compression process. Now this is the point where we are in contact with the cold energy reservoir, and therefore we have a thermal contact here, and we are releasing heat to the cold reservoir, and it's an isothermal compression process. So this is the point where we are releasing heat to the cold reservoir, and then the process is finished by a final adiabatic compression step, where again we have thermal insulation, and it's adiabatic process, therefore we don't see any heat exchange with the environment. Alright, so that completes the process. And how do we get the work by this engine? Well, this is going to be the area enclosed by this cycle. So this total area here will give us the work done by the engine. So it will be W engine. Okay, so let me summarize what we just said about these steps in the process. Now we have from A to B an isothermal expansion, temperature equals TH, isothermal expansion process, and this is the point where we are absorbing heat. So heat added to the system is QH between A and B, and the work done on the system is W A to B. And similarly, we have B to C, an adiabatic expansion, and this is going to have no heat exchange, so there will be no heat added to the system. However, there will be work done, W B to C, and then we have C to D isothermal compression that's at temperature Tc. So we have isothermal compression at temperature Tc, and this is the point where we have Qc to D. The heat added is minus Qc, it's actually heat released, and there will be a work done from C to D, and we will have final step from D to A, adiabatic compression, and this is the point where we have no heat added to the system, heat is zero, there will be some work, W from D to A. The net work done, so this is basically W engine. You can see here W engine is going to have two contributions, W A to B plus W B to C plus W C to D plus W D to A, which means the total area that's enclosed by this cycle. So we have this cyclic process, and therefore we finish the cycle and we have the total area enclosed by the cycle that's going to be equal to the work output of this engine. Now obviously this is it's very important that we note here this is a reversible cycle, therefore we can operate it also as a heat pump, right? So let's take a look at how we can express the efficiency of this cycle. First, I'm going to state without proof how we can write the efficiency of the cycle. Well, for a heat engine, remember that the efficiency efficiency of the Carnot cycle will be the useful output, that's the work done by the engine, W engine, divided by the amount of energy that we are providing into the system, that's QH. And from the first law of thermodynamics, we have for the cyclic process delta E internal for a cycle is equal to 0, because it's we are back at the temperature TH. We start at temperature TH, back at temperature TH. That means the internal energy does not change. So the total energy added to the system in the form of heat and in the form of work add up to 0. So we have the total heat added to the system is minus the work done on the system. So let me remind you, this is on the system. Alright, so what is the minus work done on the engine? It's the work done by the engine, W engine. So this is the total heat added to the system. So I have QH and there is the heat released by the system. QC is equal to W engine. So if I use this relationship to find the efficiency of the Carnot cycle is QH minus QC divided by QH, and this will be equal to 1 minus QC over QH, and we're going to show that in a moment this is actually equal to 1 minus Tc over Th. So basically what I'm suggesting is that, so let's put this as a remark here. I'm suggesting that the ratio QH over QC for the Carnot cycle is equal to the ratio of the temperatures, Th over Tc. We need to show this. So that's the efficiency of the heat engine. Now if we work on the reverse operation, that's heat pump. And remember, for a heat pump, we have two operating modes, cooling or heating. So coefficient of performance, heating mode. In the heating mode, the useful output is the energy that we're providing to the hot reservoir, it's QH, and the energy that we're inputting is W. So it's going to be QH divided by QH minus QC, and with this suggestion, basically I'm saying you can replace QH with TH, and this is going to be TH minus TC. And how can I do this? Because this is QH over QC, this is QH over QC minus 1, so it is TH over TC divided by TH over TC minus 1. So this will be equal to TH over TC times TC over TH minus TC, and I will get the same answer. Now similarly, for the cooling mode, coefficient of performance cooling mode, I have the useful output is the energy that I'm extracting from the cold reservoir, it's QC, divided by the work done on the engine, and this is going to be now similarly TC over TH minus TC, because this is equal to QC over QH minus QC. Alright, so basically this is a very important relationship. The ratio of the heat absorbed and released is Th over Tc, and it gives me the efficiency of the Carnot cycle. Operated as a heat pump, I have 1 minus Tc over Th. Coefficient of performance heating mode, it's Th over Th minus Tc. And coefficient of performance cooling mode, Tc over Th minus Tc. Now let's show that that is indeed the case. Alright, so I'm going to start analyzing this cycle. So I have A to B, temperature is fixed, temperature is Th, and therefore what is the internal energy change of the gas? The internal energy change is 0. Why is that? Because the internal energy change was only a function of number of moles of the gas and temperature. So I remind myself, for example, monatomic gas, the internal energy was equal to 3 over 2 nRT, monatomic ideal gas. So therefore it's only a function of number of moles and temperature. If the temperature doesn't change, internal energy doesn't change. The first law of thermodynamics tells me the heat added to the system plus the work done on the system is equal to 0. Therefore, I'm going to have the heat added to the system, which is what I'm calling QH, is minus the work done on the system. The work done on the system is integral minus p dv, so this will be integral plus p dv from point A to point B, and from point A to point B, since this is an ideal gas that is inside this cylinder, PV is equal to nRT, so I have PV is equal to nRTH, so this will be nRTH over V dV, so this will be nRTH natural logarithm VB over VA. So I have found what QH is, the amount of heat I'm absorbing from the hot reservoir. VB is greater than VA. Remember, this is an isothermal expansion process. It is equal to nRTH natural logarithm VB over VA. Okay, so let's keep this in mind. This is the energy that we're absorbing from the hot reservoir. Now I go to the cold reservoir, process from C to D. C to D process is at temperature Tc, therefore the same story, internal energy change is 0, and therefore I find that the energy that I'm adding to the system, Qc to D, plus the work done on the system is equal to 0. So the energy I'm adding to the system is minus the work done on the system, and this is going to be integral from C to D, and this time nRTC over V dV. So here I have PV is equal to nRTC. So this will be nRTC natural logarithm Vd over Vc. And you see Vd is less than Vc. This is an isothermal compression, and therefore I have the heat added to the system is negative. Qc to D is negative, so the amount of heat I'm extracting from the system, Qc, is nRTC natural logarithm Vc over Vd, the positive version. So this is the heat extracted from the cycle to be released to the extracted from the engine to be released to the cold reservoir. So what is the ratio QH over QC? Well, the ratio is nRTH natural logarithm VB over VA divided by nRTC natural logarithm Vc over Vd. nR's cancel, so the answer is Th over Tc multiplied by the natural logarithm Vb over Va divided by natural logarithm Vc over Vd. So I have to show that this part is 1. And how can I show that? Now I have to work on the adiabatic processes in the cycle. Alright, so I concentrate on the process from B to C. So B to C, remember, is adiabatic expansion. Adiabatic expansion. Let me remind you here, that's B to C, we have the adiabatic expansion. The temperature is changing from Th to Tc. And in this case, we have adiabatic process, so Q heat added is 0. There will be work done, WB to C. And furthermore, because this is an adiabatic process, what do I know about adiabatic processes? If it's a reversible process, PV to gamma is a constant. And if you write PV is equal to nRT, you have nRT times V to gamma minus 1 is a constant. Therefore, temperature times V to gamma minus 1 is a constant for this process. Okay, so what's the temperature at point B? Point B has temperature TH. Point C has temperature TC. And what is the volume at point B? VB. And here I have VC. So therefore, I find that TH times VB to gamma minus 1 is TC VC to gamma minus 1. And if I look at the other adiabatic process, which is the one from D to A, adiabatic compression process, here again I have no heat exchange. There will be some work done. And now at D, the temperature is TC. At A, the temperature is TH. The volume is D, volume is A. So I have TC VD to gamma minus 1 is TH VA to gamma minus 1. So if I use these two equations, I'm going to find out that, so let's put them together. TH VB to gamma minus 1 is TC VC to gamma minus 1. TH VA to gamma minus 1 is TC VD to gamma minus 1. So I want to take the ratio of these two. I will find VB over VA to gamma minus 1 is VC over VD to gamma minus 1, or I find that the ratio VB over VA is equal to VC over VD. Now what did I need? VB over VA natural logarithm divided by VC over VD natural logarithm. So natural logarithm of VB over VA is equal to the natural logarithm of VC over VD. Therefore, so I find that the ratio QH over QC is TH over TC times natural logarithm VB over VA to natural logarithm VC over VD, and these cancel. So this is going to give me the ratio QH over QC to be equal to TH over TC as expected. Therefore, I find that because I can write QH over QC as TH over TC, as I have suggested here, I can write the efficiencies using this ratio TH over TC, and the way you do that is as a shortcut, wherever you see QH, you replace it with TH. Wherever you see QC, you replace it with TC. As I have shown here, this procedure works because you can divide the top and bottom with QC and get this ratio to give you the right answer. Alright, so basically we now know what is the theoretically most efficient engine that's operating between two energy reservoirs, and the theoretically highest efficiency we can have between these two reservoirs for a heat engine is 1 minus Tc over Th. For the reverse operation, heat pump, for heating mode it's Th over Th minus Tc, and for cooling mode Tc over Th minus Tc. So this completes our analysis of the Carnot cycle.